Okay, my name is Philip Di Mello, and we will continue with our lectures. And today we're going to cover hypothesis testing. This is quite important in public health informatics and technology because we work with different hypotheses on a daily basis, and we'd like to know they are good or they are not good. They can be rejected or they cannot be accepted. And today I will show you quite efficient ways how we can do this evaluation and choose the right hypothesis. So let me just share my screen with you. Okay. And we can just go a little bit back to lecture 3 that was devoted to digital epidemiology, and also we touched based on syndromic surveillance as an early detection information system. And I told you that digital epidemiology is the same thing as epidemiology. The only difference that in digital epidemiology, we work with numerical data. So we work with data, numerical, digital data. Okay, but in epidemiology, also work with the data, categorical data, and that is only one difference. Syndromic surveillance is another thing, and it is an early detection information system. It takes data from different sources, including ER, which is emergency rooms, and it serves as an early detection information system. We would like to talk in our future lectures about information systems that we have in public health. So in the second lecture, we discussed data sources, but we haven't yet started discussing the information systems. Now, the thing is that one of the most important object in the whole data, statistical data in public health and digital also epidemiology, it is called Central Limit Theorem. So Central Limit Theorem reads that the central limit theorem states that if you take sufficiently large samples, so for example, 1, 2, 0, and so forth, so on, so many numbers will be here, 100, again, 1, and so forth, and we make samples of them, for example, 1 to 0, 2, just randomly, and calculate means, let's say 3 here, 3 here, and so forth. And we calculate means, let's say 1 plus 2 plus 0 divided by 3 will be 1, and so forth. We can take many, many means of the samples and then plot them. You will have normally distributed function. That's what the central limit theorem says. Now, I would like to show you as an example. Suppose we have a die, and die has 6 sides, 1, 2, 3, 4, 5, 6. And the probability of having, let's say, x equals 2, it is 1/6. Now, imagine that I have many experiments. So I toss the die many times. First I have 2, second I have, for example, 4, and third I have 6, and so forth, so on. I have many experiments I did. Now I have to choose samples. And again, I will take, let's say, 3, 4, or 5, let's say, elements in each sample, right? And then I make the mean of each sample, calculated means of each of samples, and I plot them. And I will get, based on the central limit theorem, a very nice normal distribution figure with a mean 3.5. Okay, and 3.5 is a mean of all outcomes: 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. This would give you 3.5. This is a mean of all of these population, of all this experiment, long experiment. But if I take, let's say, means of samples, then they will be also normally distributed with the same mean. That is the central limit theorem. So the means of my samples will be the same as the mean of the whole population. And this is a fascinating theorem. So let us see now also, and I teach central limit theorem together with another theorem, and this is called law of large numbers. Law of large numbers says that the bigger sample you take, so for example, not just 2 elements, 1 or 3 elements, 1 to 0, but many elements will be each sample, then it will be faster converged to the true mean. Okay, so this law of large numbers actually shows us that our sample should not be so small. So when it is large enough, it will be better converges to the mean, to the central limit theorem. So in other words, to the normal distribution. So that is, therefore, I just give these theorems together, because when you put them together, you see how it works. It's better. Okay, so let us see again now the my die. And as I told you, that the mean 1, 2, 3, 4, 5, 6 divided by 6, it is 3.5. This is the mean of the die. Now I take a sample, 1, 5, 6, and gives you 1 plus 5 plus 6 divided by 3. It is 4. And we know that the mean is 3.5. So I need to use the law of large numbers. The law of large numbers says that I have to take bigger sample. Let me see. So, and this experiment I did this morning, I just tossed a die, and I had this 1, 2, 5, then 2 came again, then 6, 4, 3, 2 again, 4, 5. That was my experiment. And I had here 10. So it is almost 3 times as long as this one. Now, as an initial experiment. Now, with this experiment, when you make summation and divide it by 10, you will have 3.4. And 3.4 is much closer to 3.5 than 4. So when you take, for example, 10,000 or I don't know more, you will get very close to 3.5. And this is the idea of large data, law of large numbers, or large data law. Okay, so that is the idea. Now, what we do, and I discussed, I think, a little in the previous lecture, when we spoke how to find out percentage-wise the number of females to the number of males living in the state of Maryland. Okay, the state of Maryland has population 6.041. So we have 6,041,000 people living in the state of Maryland. So almost 6 million approximately. And can you imagine that if you would like to find out the percentage-wise of females and males, you have to knock at each door in the Maryland, in towns, in small towns, in places, and so forth, different locations, and ask who is women, a number of women, a number of men. So this is very, very hard because this 6 million is a large number. So in this case, what we can do, we will use the Central Limit Theorem together with the law of large numbers, LLN. So first of all, let us take a sample 100, which is very good. Okay. And it is a number of people, both females and males, in each sample, right? And then I have to take different experiments, right? So for instance, I had here just 10 experiments. So in 2 experiments, I had this number from here to here, the number of females, okay? And here, let's say, here I had the number of females from 46, and it's percentage-wise to 46 something. Okay, so I had these numbers I plotted, and now I have this distribution. Okay, what would happen? Of course, it is not enough, 10 experiments. So let us go here and have 50 experiments about. So here is in 50 experiments, I can have already some function I can fit in this. And I will tell you in a second why it's important. So I can fit some function already here, something like this. And this, of course, is not normally distributed. It is skewed to the left. But Central Limit Theorem shows us that we need to have normal distribution. So it will be the Bell function like this. Okay, so in this case, what I have to do, I have to increase the number of experiments, which also it follows the law of large numbers. Yeah. So what I do here, I have 100 experiments, and this I have 200 experiments. So in 200 experiments, what I should do, I should question or study 20,000 people living in the state of Maryland. It's much better than 6 million, right? It's much better. Now, what happens is, in this case, I can go further and I can, for example, increase the number of experiments to 500, then to 1,000, okay? And in 1,000 experiments, I already have 100,000 people involved. Okay, and this is what I have to do. However, what we actually do, we don't do this. And I will show you what we do. We know that following the Central Limit Theorem and the law of large numbers, we will have the normal distribution, and the means of samples will converge to the mean of the population. Okay, so what I should do here, this is a function, this is a Gaussian function that describes any normal distribution. Here is sigma squared, it's a variance. Okay, and square root of sigma squared is sigma. It is called standard deviation. Standard deviation. And here is, we call it as mu. It is our mean. Okay, so what we do now, we will fit our curve into this diagram that has 200 samples, which with 100 people in each sample. So we have 20,000, and you remember. So let us do now. When we do this fit and calculate errors, which will be here, we find out that errors are so tiny that we can neglect these errors compared to the fitted curve in this diagram. And the central limit theorem, together with the law of large numbers, tells us that this curve, fitted curve, the mean or the top of that, okay, that it will here it will be the same as a mean of calculation of a population. Okay, so we did not calculate the population of 6 million. We did only that is limited number of experiments, and we fitted the curve. We did not do this here because it was 100 here, because this would give us quite a mistake, big error when you fit this. But here we have very, very small mistake, and we show that the number of females, so the number, yes, it outnumbers the number of males, and the value of that, it is 51.3 approximately what we have here. Okay, so we didn't go any further when we just fitted this curve normal into this distribution that what we collected, okay, on 20,000 people, and we had a very accurate result. Okay, so now what we do, we have a z-score. Why we do z-scoring? Because z-scoring is very convenient to us. And also z-scoring standardizes data. Because what I show you, when we talk about data, let's say pre-processing and processing, a very simple data set, let's say height and weight. So we can take, for example, 5.8, so 5 feet 8 inches, and it is 190. This is 5 feet 5 inches. It will be 120 and so forth. So this one will not work well when we apply, let's say, different algorithms. And we need to standardize the data set. And z-scoring exactly does this score. Okay, so it is a part of pre-processing. Now, what we do next, so we have this value, which we transform to z. And this is a mean, and this is standard deviation. Standard deviation, okay. So now we have here mu equals 0. We have 0 mean. But what is interesting, that now any kind normally distributed function will be presented in this way. You have here about 68% of all data between plus sigma and negative sigma. We have between this and this, we have, it is 2 sigma. This is 4 sigma. So this will be 95. We approximate. So 95% of all data will contain within this segment. And then we have 6 sigma. We have 99.7. 99.7. So this is, it's approximately. So this magic numbers, as I told you at the previous lecture, that if you wake up any data scientist, he or she will tell you right away these numbers. After this scoring, after this score transform, because this is quite useful for us, and we shouldn't worry about any talking about any normal distribution. It is very cumbersome. So, but when we do transformation, this score, you have all normal distribution, all distributions will look like that. It is very, very good. And here, yes, you just worry about this data. You can process the data, but they all will be 68% in between the first standard deviation. Now, what is interesting, that as you remember, I told you that many, I don't know, the infinite amount of different examples show that these examples, for example, high distribution of, in the United States, of males, weight of newborn children, whatever, it's all they obey this rule of normal distribution. But sometimes it is not true. And we have distributions differently. For example, you remember I told you this is uniform distribution of death of bacteria. So if you take a bacterium here, it will die between 1 and 5 hours. And if you take a bacterium here, for example, it will also die between this. That can be described as a uniform distribution. A uniform distribution is not normal distribution. So this is give us more work to do. But the central limit theorem says that if I take, for example, one bacterium here and one bacterium here, so 1 and this number, let's say 3. So I take these 2 bacterium, it will be, let's say here it is 2, let's say 0.05, for example, plus this will be 4.1, and then I will do division by 2, so I will see the average. So it will be 6.15 divided by 2. And then I take many averages. I will get something close to normal distribution. Not exactly, but something close if I plot these numbers. And of course, here I forgot the law of large numbers because I have only 2 elements in each sample. It's not enough. And what actually it's from, let's say my experience too, when we work with public health data, we should have at least 30 elements in each sample, at least. Okay, that's what algorithms that I used to work with, but maybe some other algorithms, they have no this rigid requirement, but the algorithm I worked with, they require over 30 elements. However, when I do this and I calculate the means and I plot these means, I will have curve, something like this. With a mean value 3. So I use here central limit theorem. So I calculated samples of 30 bacteria in each sample, and I had many samples, and I have perfect normally distributed curve. Okay, now, however, some people say that, oh, it is just approximation because uniform distribution here is 0, and here you say that you will have something. Yes, it is true. So I will have something here, and we will just solve what we will have. So mean of this uniform distribution will be 1 plus 5 divided by 2, will be 3. And variance will be this, 5 minus 1 squared. It is divided by 12. So it will be 1.33. This is a variance of a uniformly distributed function. So when I take square root of 1.33, I will have 1.15. Now we go to calculate z. In this case, we have 1.74. So 5 minus 3 divided by standard deviation. It is 1.74. Okay, so what we'll have here, we'll calculate now the probability that this bacteria can live longer than 5. So 5 minus 1 divided by squared by 12, 16, 2, 133, and this is, I will have, this is variance, this is standard deviation, and I would like to know this probability that this bacteria will live longer than 5. So it is 174, and I go to this table. So it is 17, and I have 4 here. It is 95907. 95907. Okay, so this is 7. Well, it doesn't matter. So this is a probability. When you remember, we discussed in lecture number 2 that the data will be less than 5. Okay. Now we have here the probability 9.5, but what the probability will be if bacterium lives longer than 5 hours? I have to subtract from 1 because the whole thing is 1. It's under this curve. The area is 1. So I have to subtract this probability from 1, and I have 4%. So the probability that a bacterium live longer than 5, it still exists. It is only 4%. So 4%, the probability. Okay, so 96% bacteria will die before 5 hours. Now we take another example. So suppose we have syndromic surveillance, and it results in average of 220 infected every day people. So suppose you work in a county, and you work for a public health agency, PHIT, we call. And your supervisor says, I want to, so you calculate how many people living in our county but infected, And is there a probability we're having 300 infected tomorrow? So it's a big jump. So you did this work. It is syndromic surveillance because it is also your data. And you know mean value, you know standard deviation. And what you have to do only to calculate the Z score. So in this case, it will be 300 minus mean 220 and divided by 25 from our formula. So you will having over 300 infected tomorrow. Let's see now. So when you do this calculation, you have 3.2 Z. And we also find this in our table, this one, 3.3. And you will see that the probability of having 300 infected tomorrow is only 0.7%. So it's very, very small. There is probability, but it's very, very small. So you have to say your supervisor tomorrow, the probability of having 300 infected tomorrow is very, very small. It's less than 1%. Okay. Now, let's talk about hypothesis testing. This is quite important. So the first step in hypothesis testing is to calculate the test statistic. Okay, the test statistic, there are two. It is Z we know, and T statistics. Okay, this is Z statistic and T statistic. The formulas for the statistics are the same except one thing, and I would like just to tell you that. You have Z equals X minus, when you calculate, minus mu divided by S divided over the square root of N. N is a number of samples. And in this case, when I say S, it should be sigma, because sigma is the standard deviation of the whole population. So if you know this, please, you have to remember that. Know this, if you know this, standard deviation of the whole population, use Z transform, Z statistics. In T statistic, there is a big difference. It is X minus mu is a mean of a sample, and here is S over square root of N. Okay, so this is very, very important. So if, for instance, you do not know the standard deviation of the whole population, you use T. If you know, you should use Z. There are many ways to know standard deviation of a population, but in many cases, you have no chance to know this. So you have to use T. And T has different tables, and I will show you how, without any calculations, to answer a question, we should reject the hypothesis or accept it, okay, without any calculations. Okay, let's show you. So first of all, we should talk about confidence level. So what is confidence level? Confidence level can be 0.9. 0.9 means that we can give you an answer, but we leave the right to make 10 mistakes. So there is 10 mistakes out of 100. Another confidence level is 95%, or we make 5%. 5% of mistakes we can make. And here we can make only 1%. What is interesting that this is empirical, there is no theorem, but it was common adoption. We say that we use in statistics all the time this confidence level. Very rarely we use this and this. We do not use them. So this is sometimes we use, but not this one. So usually we take 5%. So 5% means that we make a mistake. Okay? Now, the thing is, you also have to know what does it mean statistically significant result. Because when you do any work in public health or in healthcare, okay, you should calculate you should tell that it is within statistically importance, or it is just something that might happen in random. Suppose you work in a hospital and you have a new technology that maybe subsides some symptoms, that it just decrease the number of symptoms. So if, for instance, it is less than confidence level, so we can say, for example, it is confidence level, it falls below 5%, so 3% or 2%. We'll discuss it now. So this is statistically significant result. But if, for instance, it is over that, so it is, for example, I don't know, 10, 15%. So this can be random. So it is just a chance. So your technology somebody brought to your hospital maybe just randomly eliminated some symptoms counting and something like this, but not statistically significant. So this is quite important. In the case of normal distribution, it sounds like this. We call alpha, it's a critical value. It is 0.05 or 5%. So all this thing is random. This is, we have significant. It is one-sided, but can be also two-sided. So in this case, it is random area. So whatever you make a conclusion, suppose you do some research in public health and you found out that there is some outbreak. So maybe just your studies it has some randomness and they have very little significance in terms of statistics. Now, suppose you have epidemiologist tested 100 individuals and 5 had high fever. Okay, so population standard deviation is known and is 2. This one, it was given you by a hospital. So the standard deviation is 2 of the population. So this one, if it is known, it is Z statistic. Z statistic. And you go and calculate this Z. You have 100 people in one sample, or 100 patients, and your Z is 10. And what is a null hypothesis? A null hypothesis says that, for example, null hypothesis, that it is not 5, but 3 out of 100 are infected. And 5 is not correct, it's random. Okay, let us calculate now. So somebody says that 3 is a correct answer, and we take it as a null hypothesis that we would like to check. This is called null hypothesis that we would like to check. It is 3 And we calculate this using Z. Why? Because we know the standard deviation of the whole population in hospital. It is 2, and we have 10. So when we go to 10, the our table of p-values, because you remember we spoke last in lecture 2 about what does mean p-value. This p-value is p-table. When you put 10, it corresponds to 1. So we have two-sided curve. Why? Because we test if 3 is correct. 3 can be a little bit more or can be a little bit less. So when we have exact number, we should use two-sided normal distribution. When we have, we already discovered this. If we have something bigger or smaller, we have one-sided. And so it is smaller or bigger. Okay, but if we have just one number, it has to be two-sided. So it is 2, 10 corresponds to 1 on the Z table. 1 minus 1 is 0, and 0 is less than 0.05. So it is in this gray area or red area where it is statistically significant. Okay, so in this case, all hypotheses should be, null hypotheses should be rejected. There can be many hypotheses, but in this case, it is 3 null hypotheses. This is rejected, and this is not correct. In this hospital, we see that that this one is not good hypothesis. That, for instance, tomorrow will be 3 patients in the emergency room out of 100 with high fever. It can be more than that or less than that, but not 3. Okay, so this, you reject this. But if you'd like to find out more or less, you have to use one-sided Z transform. But it's okay, the same thing. Now, what I would like to tell you, if, for instance, population standard deviation is not known, you work in a hospital, and they say, we don't have it. Didn't do historical data, no standard deviation of the population, we don't know. Do whatever you want. In this case, you have to use t-test. In this case, you use t-test because we do not know sigma. We do not know this population. And instead of sigma, we use S. And S, it is standard deviation of your sample. We have no other solution. Okay, and I would like just to show you an example. And it is very, very simple because many students who attended my classes and other classes, they say, oh, it is so difficult to understand. So T statistic, Z statistic is simple, but T, it is nothing difficult. Okay, so let us see. First of all, we have to do null hypothesis. Null hypothesis, okay, it is systolic BP mean is less than 140 or equal 100. So we would like to say, so the hospital officials say that we have a new medication that decreases systolic blood pressure, and please try to find out whether it works or not. So without your help, they will not do this because it can be random. So you have to find out. Can we reject this, or we can say it is true? You know, this medication is so nice, it reduces blood pressure. Okay, so what you do, you take sample n greater than 30, because for T test we need to be very accurate, 30. But I will show you now that it is not true. We can even take a bigger sample, because T statistic actually mathematically was proved with a number of samples not more than 30. But we can use T statistics for infinite number of elements. I will show you now in a second. Now we have sample n 100. Okay, and then you calculated the mean 145 with a sample standard deviation 15 because you do this experiment. Of course, you know your variance and you have sample standard deviation, so you don't need to ask the hospital give you a sample of the population of all these patients who were in this hospital for 10 years or 20 years. You know, we don't need it. Okay, then but we have to use this T statistic, not Z. Now, it is number one. We found no hypothesis. Number two, we collected data. Okay. Number three, we have to determine the level of significance. It's always 0.5, which is 5%. Okay. And then, of course, use what statistic will be. And the statistic is T because you have sample standard deviation, non-population sample. So it is T statistics. So you need to put here 15 divided by 100, and you have 3.33. Now, what we do with this? And I tell you that with this one, we can solve so many problems in health care you cannot imagine. With Z or T statistics, we can examine medications, we can examine different lab tests, anything you want. Okay, now we go, as I said, fast method. So fast method is the following. In T test is another parameter which is called degrees of freedom. Degrees of freedom, df, equals the number of patients in a sample minus 1. Since we have 100, we don't worry about it because here will be 99. 99, this table doesn't have 99. Or you can take 100, for example. You won't make any mistake. Okay. Now, what we do here, we have to find 3.3. Let's see here. 3.3 is right here. 3.3, it is this one. Okay, it is 3.390, and we have 3.3. Okay, and then it's another one, which is 1,000 samples, will give you 3.3. Okay, so this is in between these numbers. Look very carefully. Between 3,000, 3.3 and 3.9. Between these numbers. Okay. What happens here? What happens here? That it is a degrees of freedom. But when you have 100, you have to calculate, you have to compare also these numbers. So this is 2.871. And 3.339. So it is in between this, but closer to here. And it is in between this and that, but we will choose this one because this is already corresponds to bigger samples. But you see that they take bigger samples, they do not change much T statistics if you have 100 or more. But if you have 30, okay, 29, 28, 30, and then after 30 you have 40, 50, that's exactly what I told you. So more accurate results you have here. So this is for us is more than enough. But look at that. Now without any calculation we can show this is our significance level. It is 5%. To the right to this will be statistically significant because it is less than 0.5. It is 0.25, 0.1, 0.1. It is statistically significant when we reject the null hypothesis. And here is when we accept null hypothesis. In our case, we are on this line somewhere between this and this, but closer to that. So it is in the area of rejection. So conclusion that we have to reject this hypothesis, null hypothesis. And null hypothesis says that the medication they have that decreases the reading, systolic reading blood pressure, and it becomes less than 140. You should reject this hypothesis and say that it's not true. It will be more than 140. So maybe this is not so good news for a hospital, but this is the correct answer. Okay, so we finished today, and next time we will talk about interesting things, and also we will start working on, I will explain you the fundamentals of Python, because then we will start working on data pre-processing, and we will work with real raw public health data, and you will have the whole spectrum of data pre-processing. And we will use Python programming. Okay, bye-bye.